Hi everyone, and welcome back to our YouTube channel. In this lecture, I will continue to show you the solution of homogeneous systems, and I will continue to give you an additional example. Okay, suppose here is our example. So let's write a homogeneous system and try to find its solution by the method that we learned in the very previous lecture. And let's say here's the system of equations: x1 minus x2 plus x3 and say plus 2x4 is equal to 0. And another equation, let's say it is 3x1 plus 2x2 minus x3 and plus x4 is equal to 0. Alright guys, let the homogeneous system be given in this form, and what we're asked to find, as usual, find the solution set of this homogeneous system. And why is this system homogeneous? Because the right hand side values are all equal to zeros, right? That's why we call this system homogeneous. And it needs a special treatment to find the solution. Okay, let's start the solution. And how would we start? Well, the very first step is, right, okay, we are trying to find the solution set X. And the solution set is what? And the solution set is nothing but the 4 tuple, right? So we are trying to find the values or the form of the general solution, which includes this 4 unknown variables: x1, x2, x3, and x4. So this is what we are looking for. All right. Okay. And the first step is what? The first step is to express our system in the matrix form. Well, in the coefficient matrix form actually, because we don't need the right hand side values, right? Because all the right hand side values are equal to 0, and taking them into account doesn't change the value on the right hand side, so no need to write them in the matrix form. Alright then, I just write the coefficients of each equation. So these are the coefficients of the unknown variables in each equation, and this is for the first equation as always. And for the second equation, I write their coefficients here: 2, 3, 2, minus 1, and 1 again. Okay, this is the first step. This is the coefficient matrix form of the system. And in the second step, we prefer applying a technique to reduce our coefficient matrix into either row echelon form or reduced row echelon form. In other words, we will apply either the Gaussian elimination method or the Gauss-Jordan method. Suppose we apply Gauss-Jordan method, and therefore we need to convert our coefficient matrix into that of row echelon form. And of course, how can I do that? So I look at the matrix and the pivot element in the first row. Well, first row is a non-zero row, then the leading entry in the first row is my first pivot, which is 1, and I need to eliminate all the values below that pivot element. So that's only 3 here, so we need to replace row 2 by row 2 plus minus 3 times row 1. Okay, then what I get? Our matrix becomes 1, minus 1, 1, and 2. This is the first row, and values in the first row remain unchanged. since we didn't perform any elementary row operation there. And the second row becomes 0, 5, minus 4, and minus 5. Alright? After each step in the elimination process, I check to see that if the matrix is in the row echelon form or not. And if we take a closer look at the matrix we obtained now, you see this is the pivot element, and this value is now 0, and we have a strictly increasing number of zeros from top to bottom. So now we have the row echelon form. Then we're done with the elimination process. Okay, so we have our row echelon matrix here. And how about the third step? Then the third step is to compute the rank, right? We need to find the rank of this row echelon matrix. Okay, and how would we find the rank? Just as a quick reminder, if you want to find the rank, we reduce our matrix to either row echelon form or reduced row echelon form, doesn't matter which technique we use, and then count the number of non-zero rows, or the number of pivotal positions, or the number of basic columns, right? Whatever we want. So if I look at this matrix closer, I see that all the rows are non-zero rows, so we have 2 non-zero rows, which means we have rank is equal to 2, right? The rank of this row echelon matrix is equal to 2. And why is this value important for us? Because actually our main concern is not only finding the rank, but also determining the number of basic variables and free variables, right? And how we can find those numbers? Well, first of all, we need to find the number of free variables and basic variables that we will be using in the form of our general solution, and then we will determine explicitly what these variables are, and then continue to write the basic variables as an algebraic sum of the free variables. Okay, then we have n minus r number of, and in other words, the number of free variables is equal to n minus r, right? So this number is important. And what is n and what is r here? N is the number of unknown variables. And how many unknown variables we have in this system? We have 4 unknown variables: x1, x2, x3, and x4. So the value of n is equal to 4. And how about r? And r is the value of rank, which is 2. So 4 minus 2 gives us a 2, which means the number of free variables, okay, which is very important to form the structure of general solution, right? The number of free variables is equal to 2. These are the free variables, the number of free variables. And how about the basic variables? Okay, as we see, we have 4 unknown variables, and 2 of them are free variables. So the remaining ones are the basic variables, but nothing, right? So again, 4 minus 2, we have 2 basic variables. All right. So again, by a step-by-step procedure, we apply this computational process so as to produce the general solution. And how about the next step? So say the 5th step, right? So now we know how many free variables and basic variables we should have. The next step is to decide which variables are the free ones, whereas which variables are the basic ones, right? So how would we decide that? Well, again, we look at the row echelon matrix here and find the pivotal positions. So, well, let me use a different color to highlight the basic columns, and the first column is a basic column. And why is that? If you remember the definition of the basic columns are the columns in the row echelon form or the reduced row echelon form that correspond to the pivotal positions. In other words, actually, we are looking for the columns that include the pivotal positions or the pivot elements. And these columns are the basic columns, right? So this is the basic column. So this is the basic column, one of the basic columns actually. And also we have 5 as the second pivot. How do I understand that? Because second row is a non-zero row, and the very first non-zero element in the second row is 5, which means that this is a pivot element as well. So the second column is also a basic column. Are there any non-zero rows? No, we have only 2 non-zero rows, and therefore we can have at most 2 pivotal positions, which means we can have at most 2 basic columns, which we already have found. So how about the remaining columns, the third and fourth? So the third and fourth columns are the non-basic columns, right? These are the non-basic columns. Okay, now I can decide which are the free variables and which are the basic variables. And what is the basic variable? A basic variable is the one that corresponds to the basic column. So in other words, as we all remember, each column here in this matrix actually represents the coefficients of one unknown variable. So the first column actually represents the coefficients of unknown variable x1, whereas the second one represents the coefficients of the second unknown variable, and the third one is the third one, and fourth column represents the fourth unknown variable's coefficients, right? So since the basic columns are the first and second columns, then x1 and x2 are called the basic variables. Why? Because they correspond to the basic columns. In other words, the basic columns are associated with the coefficients of these unknown variables, right? These are the basic variables. And how about the free variables? How would we decide that? Well, that's even much simpler. After finding what the basic variables are, then the remaining variables must be free variables. So free variables are those variables that corresponds to the non-basic columns, and in this case x3 and x4, right, unknown values x3 and x4, the third and fourth unknown variables, are associated with the 2 non-basic columns, the third and the fourth columns. This is of our concern, and these are the free variables. Okay, now we know what the free variables are and what the basic variables are as well. And the next step is, after finding out which of these variables are basic and which of these are free, the next step is, so we need to express the basic variables as a linear combination, or what is called as an algebraic sum of the free variables, right? So how can I do that? Well, I look at the row echelon form again, starting with the last row, and in the last row what I have. So I'll just write it back, and I will apply back substitution method, right? So I got, if I look at the second row in the row echelon form, I got 5x2 minus 4x3 minus 5x4 is equal to 0. So since x3 and x4 are free variables, then I move them to the right hand side of the equality, and this yields us what? 5x2 is equal to is equal to 4x3 plus 5x4. And one thing only left for us to finish this algebraic manipulation. So to finish this sequence of arithmetic operations, I need to divide both sides by 5, which is the coefficient of the second unknown variable. Okay, and it gives us, dividing both sides by 5, okay, x2 is equal to 4 over 5 x3 plus x4. And that's good. That's good because we already obtained one of the basic variables in terms of two free variables, x3 and x4, right? x3 and x4. So in other words, I express the basic variable x2 as an algebraic sum of two free variables, namely x3 and x4. And also I need to write the other basic variable in terms of these two free variables. So again, this time I look at the first row in row echelon matrix, and what I need to do is, alright, so let's do it here. I know the values, so I write the first one, and what we get in the first row, we got x1 minus x2, so I just apply back substitution method as always, plus x3 and plus 2x4, right? So x3 and x4 are the free variables, so is equal to 0. And how would I write this? I look at the first row, right? So you see, I look at the first row, x1 minus x2, x3 plus 2x4. Alright, and let's continue with our computational process here. Now x1 is equal to what? We already found the value of x2 in terms of free variables, so I just write it them. I just write it here, right? 4 over 5 x3 plus x4, right? This is the value of x2, and minus x3 and minus 2x4. And what we get? We have 3 x3s here, we have 2 x3s here, we have 2 x4s here. So summing them up, what we obtained is this: x1 is equal to minus 9 over 5 x3 and minus 3 x4. And this is actually the interpretation of the other basic variable x1 in terms of x3 and x4, which are the free variables. Alright, now how about the next step? Well, we are almost done, and the seventh, and maybe we can call the last step. Okay, let's put our number here. So we know that our solution is in the form like x is equal to x1, x2, x3 and x4, and all we need to do is just plug the values we have found so far. So x1 and x2, we know their values. So x1 is minus 9 over 5 x3 minus 3 x4. And how about x2? x2 is 4 over 5, right? We know its value. We have just found it here above. 4 over 5 x3 plus x4. And since x3 and x4 are free variables, I just put their values here, right? x3 and x4. And this is the structure of the general solution. So we are almost at the point where we can form the general solution in terms of free variables and particular solutions, right? So what is left to do is we need to decompose it into some algebraic sum, right, where we have x3 and x4 as the coefficient of the matrices. So how would I do that? It is simple. So I take into account this column and I take into account this column as well, right? So here's the thing. So suppose this is the coefficient matrix of the free variable x3. So minus 9 over 5. Why? Because it is the coefficient of x3, and 4 over 5, another coefficient in the second row, and 1. And now what this? This is 0, right? So this matrix times x3. And if you notice, how would I write that? If I multiply x3 by all of these coefficients, I find the same component of the matrix. But this is not enough. So plus, we also need x4, right? This is the other free variable. So how about this? And I write the coefficients of x4 in the another matrix, right? Which is left behind, minus 3. Why? Because this is the coefficient of x4 here. And plus 1, right? This is another coefficient. And how about here? We have x3, so this is 0, right? This is not the coefficient of x4. And the last value should be 1. And again, this is the coefficient matrix of x4, the other free variable. You see, if we multiply these values by x4, we obtain the same component of the original matrix. So what we do is just we decompose the form of our general solution into an algebraic sum where we have our free variables as the coefficients. Okay, and now here's what we have found, right? So this is our general solution. And as we all remember, a general solution for a homogeneous system is something like, we are looking for a solution like this if we have xi's, which are the free variables, and ci's, which are the particular solution. Actually, we are trying to find some sort of algebraic sum in this form. If we have k different number of free variables, then we have a general solution in this form, where each ci here is a particular solution. So which means that, for instance, for our solution, if I take the value x3 is equal to 1 and x4 is equal to 0, then what I have in this situation? And x4, if I multiply 0 by all of this value, we have all zeros, and summing up zeros with the x3 here gives us the x3 itself, right? This vector. So this matrix comes out. So this is the solution, which means that this also satisfies the equation, right? Alright guys, now we know how to find the general solution, or how to find the particular solution for a given homogeneous system of linear equations. Okay, then let's do another example. Well, in the examples that we have made so far, as you see, we always have had the infinite number of solutions, right? But this might not need to be always the case. So let's make another example. So here's another example. Okay, let's see what we have here. Now suppose this is the new system. Say x1, alright, x1 plus x x2 minus, right, x2 minus x3 is equal to 0, and 2x1 plus 2x2 alright, minus 2x3 is equal to 0. And let's define one more equation. 3x1 plus 3x2 minus 4x3 is equal to 0. Okay, now suppose this is the new system given to us for finding a solution. Okay, and let's find the solution. So we're looking for x1, x2 and x3. So we need to find this 3 tuple. Okay, right, so we need to find this 3 tuple. And what is this value? Okay, again the same procedure will be applied here. Okay, so again we need to write the coefficient matrix and then reduce it to the row echelon form. Okay, right, just write down the coefficients here. 2, 2, minus 2, 3, 3, minus 4. And now we have the coefficient matrix, and now let's apply elementary row operations. Right, so I replace the second row by row 2 plus minus 2 times row 1, and I replace the row 3 by row 3 plus minus 3 row 1. So performing this elementary row operations, our matrix becomes, let's see what it becomes. Here we go. So 1, 1, minus 1, no change in the first matrix, in the first row, sorry. And the second row becomes 0, minus 2 and 0, and the third row becomes 0, 0 and minus 1. And after performing this elimination, I check to see whether or not the matrix is in the row echelon form now, and yes, the answer is yes. We have a row echelon form here, right? We have the strictly increasing number of zeros, as we all notice. Alright then, so let's see. Now what we have. Now what am I going to do? So I compute the rank, right? So what is the rank? What is the rank here? I look at the row echelon form, and the rank is what? And the rank is the number of non-zero rows in this row echelon form. How many non-zero rows do we have here? So we have 1 here, 1 here, 1 here. So which means all the rows are non-zero rows. So we have 3 non-zero rows, which means the rank is equal to 3. And how many free variables we have? So we know that we have n minus r free variables. In this case, we have 3 unknown variables, right? x1, x2 and x3. So 3, and our rank is equal to 3. So 3 minus 3 gives us 0. Then what it means? Is it strange to find the number of free variables equal to 0? No, it is not. It is one of the possibilities that we can run into while trying to find the number of free variables or the basic variables, right? But what it means for us in terms of finding the general solution, This is the key point to take away with you. So this is the actually main reason why I give this additional example. So I want to highlight one important point here. If we have here in this case rank equal to 3, which is the unknown, which is the number of unknown variables. In other words, rank of the matrix is equal to the unknown variable, the number of the unknown variables. So in this case we have no free variable. But if we don't have a free variable, then how can we form the structure of general solution? Because if we have an infinite number of solutions, then we need to form this structure, right? I need to express the basic columns in terms of the free variables. So the basic variables should be written as an algebraic sum of the free variables. But in this case, we have no free variable. All the variables are basic variables. So in this case, we don't have an infinite number of solutions, guys. There is no infinite number of solutions here. Then what is the solution here? If you remember in the first lecture related to systems of homogeneous equations, in other words, in the previous lecture, we have the trivial solution case. So we know that we are ensured to have at least one solution, which is called the trivial solution. And what is the trivial solution? And the trivial solution is the one which includes all the zero values, right? So in other words, if you have no free variable, in other words, if the rank is equal to the number of unknown variables, then we have only the trivial solution here, which is nothing but all zeros. So x is equal to 0, 0, and 0. These are the values of 3 unknown variables, and we have the trivial solution case. So we don't have infinite number of solutions here, okay? Because no free variable. Rank is equal to the number of unknown variables. And how about understanding that by applying back substitution method? Can we decide that by applying back substitution method in the row echelon form? Yes, the answer is yes. Let's take a closer look at these rows. For instance, in the last row, what we have? If we apply back substitution method, what we obtain? So we have minus x3 is equal to 0, right? How do I understand? Because I started at the last row and applied back substitution method. I plugged the values, right? So what it means? This means that x3 is equal to what? 0. And we move one step above. So we pass to the second row. Okay, what we got in the second row? We have minus 2 x2 is equal to 0. And how would that happen? The only possibility that this equality holds when x2 is equal to 0. And in the same manner, if we move to the top row, right, what we get here? So we get x1 plus x2 minus x3 is equal to 0. And we know that x3 is equal to 0 and x2 is equal to 0. Then the only possibility that this equation holds is what? Is when x1 is equal to 0. You see that? Right. So we have the trivial solution case in this example. We have only one solution, which is the trivial one. And if we take the values of all the unknown variables equal to 0 and plug them in this equation, in these equations, they will be all satisfied. All right. We now understand what does it mean for a homogeneous system to have only trivial solution, right? If we have no free variable, or if the rank of the row echelon form or the reduced row echelon form is equal to the number of unknown variables, then we have only the trivial solution that satisfies this homogeneous system. Alright, before finishing this lecture, guys, I would like to get to the point that to the solution set of the above equation, right? If you remember, we found a solution here like this, right? A linear combination or as an algebraic sum. So here x3 and x4 can take on any real values. So what this means is, let me explain it a little bit before finishing this lecture for you to clearly understand what we have found. Okay, suppose x3 is equal to 5 and x4 is equal to, say, 2. Okay, and then when we put these values, x3 is equal to 5 right here and x4 is equal to 2 right here, and then multiply these values, then I find a solution. But don't forget one thing, we have an infinite number of solutions, and as the values of x3 and x4 range over some set, which is the real set, of course, the set of real numbers, then we have many infinitely solutions. So in this case, if we put the value x3 is equal to 5, then in the first combination, in the sum, what we get multiplying by 5 yields -9 here, 4 here, right, 5 here, and 0 here, plus what? Plus, if you put the value x4 is equal to 2 and multiply it here by each term, so we have -6 here, 2 here, 0 here, and 2 here. And if we sum this up, okay, we apply element-wise addition, so which means -9 plus -6, which is equal to -15, right? This is the element-wise addition. So we sum the elements associated with the same position. So 4 plus 2 is equal to 6, 5 plus 0 is equal to 5, and 0 plus 2 equal to 2, which means this is a solution. This is just one solution among the infinite number of ones. So we have infinite number of solutions. This is only one of them. And if you change the values of these free variables, then the solution also would be changed with respect to the values of free variables that we have chosen. Alright, guys, I believe that you clearly understood what I mean by that. Okay, and finally, we know how we can find the solution of homogeneous system and the different possibilities that we run into, right? So we are also now familiar with the different possibilities that we can run into while trying to solve a given homogeneous system. Alright then, that's it for this lecture, and see you in the next lecture.